Okay, so welcome to the last day of this class. This is your final lecture. I've saved for the final lecture this term something that is probably more useful and more relevant to people who either have more experience with R than sort of the average person in this class, or who have more experience with statistics than the average person in this class. So up until this point in the class, I basically assumed people have no statistics training at all, nothing. This class is on working with model results, that is model results from statistical models. So if you don't know how to do any statistics or run any models, this class is useless to you. But most of us have some statistics training in our class, or are going to get a bunch of statistics training. And what you will learn in almost all of those classes does not include nicely displaying results from those models. You'll typically learn how to fit the models, what are the assumptions of those models, their restrictions, that sort of thing. How to interpret the results, but the results you're interpreting are usually sort of the raw output from those models. If in certain classes you might learn how to present them visually or something, but often the methods that are taught for visually presenting results from models are clunky or outdated or problematic for some other way. So today I'm going to talk about ways that are relatively straightforward methods for getting usable results out of your models, formatting them in nice ways, plotting them, presenting them as both plots and tables. So what we're going to go over today are a number of different packages that are all fairly advanced ways to deal with model results. I'm going to start with the broom package, which is for turning model output lists into data frames. So pretty much every model you would run in R, its output comes out as a list, a really large nested list with a ton of things inside of it. This is great if you need all the specific items that are inside of it, but, you know, most of the time when we're running statistical models, we only want specific components from those models. We typically want something like the fit coefficients or parameters, some standard errors, maybe p-values or something like that. Maybe we want to extract a variance-covariance matrix or something like that, but we don't need the massive amount of data that are in there because we're not, say, writing some sort of R package that needs to pull on all that data to put something together. We just want sort of the summary stuff. What Broom does is it takes those output lists, grabs only the most commonly needed information, and produces data frame summaries of those models. So rather than coming out as lists, it'll be nice one row per model data frames, or it'll attach additional data from those models to your existing data frame. Handy stuff. Next I'm going to talk about is the ggeffects package. The ggeffects package is for plotting marginal effects from models. Like how can we plot expected values for variables over the range of some other variable. So if you had this particular value of x in your model, what y would we expect to see? Or given some value of x and z and k, what would be the value of y? So this is doing counterfactuals, which I'm going to talk about, and plotting marginal effects. Sometimes you might have models that are too complex for ggeffects to handle, so you might have to do manual counterfactual plots. This is actually plotting marginal effects or dot plots, predicted probabilities and stuff, by doing all of the math, all the calculations manually. I'm going to go through that. It's an advanced example, and I expect most people will not have to do that. But if you want to know how to do it, I've done a lot of it, and I have a pretty compact, straightforward way of doing it compared to how you might do it if you had to figure it out yourself. Then we're going to change gears and talk about tabular results. So I put tables after all this stuff on plots and summary stuff because, in my opinion, that's kind of like the order of how you should be presenting things. Plots are almost always better than tables. You'll have these nice, beautiful tables in articles of results. If it's anything other than a linear model, most people are not going to interpret your table results correctly. It's just that most people who think they interpret parameters from, say, logit models or GLM models, you're usually wrong. And so those tables are not usually as useful as people think they are. And I'll talk about that a little bit. I'm going to try to do it using basic tables with Pander, more advanced tables using SJ table, and I'll touch a little bit on how to produce LaTeX tables, but I'm not going to go into it because that's a rabbit hole. And then we're going to wrap up the course because, of course, today's the last day. Okay. So, the Broom package. Broom is a package that tidies up the output from models like LM, GLM, LMER, GLMER, all that kind of thing. It only has about 3 functions that you really would directly use yourself. There's a lot of other packages in the tidyverse that call on broom to do stuff behind the scenes. So it has a whole bunch of other functions in it, but these are the ones we would typically use ourselves for working with model results. They are tidy, which creates a data frame summary of a model. Augment, which takes things like fitted values from model, residuals, that kind of stuff, and adds them to an existing data frame. And glance, which provides one row of fit statistics for your models, which is great if you want to run a whole ton of models and see which one fits the best or worst or something like that. So the broom package is library broom. Will run it if you have it installed. Okay, so models like LM and summary run on LM by default produce lists as their output. Lists cannot go straight into tidyverse functions like ggplot or something like that. So if you wanted to plot your coefficients, you would need to transform the output from your linear model in some way to pipe it into a plot. So this is the summary output from a linear model call. You run summary, it'll show something like the call, which was the actual function call that was run to run this model. It'll show a summary of residuals. It'll show coefficients with the estimate, standard error, t-values, and p-values, and some additional information on the overall model, like the multiple r-squared, adjusted r-squared, f-stats, yada, 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 right? This is normal summary output. For other types of models, even closely related models, so this is me just moving from an LM here to a GLM model. This is in this particular one, it says family equals binomial, link equals logit. This is a logistic regression model. If I run over this model and put it into summary, I get similar results, but they are not the same like fields in a list that there are for the LM. You'll see here, I now have something called deviance residuals instead of a residual summary. My coefficients have different columns in it. I now have a z value and a p greater than z column instead of t values, because GLM is always going to be on z values because it makes a stronger assumption about the structure of errors. Significance codes here, dispersion parameter here. This is something that doesn't exist at all in the LM because, yeah, it's not parameterizing that. So if I wanted to write a function that would take the output from an LM model and this GLM model, I would have to come up with some sort of special case code that would say, oh, if this is an LM, grab the t-value column, but if it's a GLM model, grab the z-value column. These might not even be in the same positions in different summary methods for different models, right? This is problematic. Things are not uniform, and every model you would run in R would probably have a completely different layout of these things. And this is just on very simple models. If we go to something like hierarchical linear models, you have an entire another range of parameter estimates that might pop out, much more complex models. The same function call would not be able to access the same stuff between them, right? Okay. Well, what tidy does is if I take a model like LM1, I could either run LM1 inside a tidy or pipe it in. It's exactly the same thing. Tidy will produce the same output for any model you give it, and it comes out as a data frame. So if I send this LM model into tidy, what I get out is I get one row for each parameter in the model. I get a parameter estimate, a standard error. I get a column called here statistic. So instead of saying a t-stat or a t-value and a z-stat or a z-value, it just says statistic because it assumes that, well, one, we know what it is, and two, we might want to stick together models. Some have t-statistics, some have z-statistics, but we want to be able to merge them with the same column names. And then it still produces a p-value, right? So even though the GLM and the LM produce sort of different output, Broom will always spit out something that looks exactly the same. If I send GLM1 to it, it's exactly the same stuff. I have a term, which is the parameter, an estimate, standard error, statistic, and p-value. So what Broom is doing is it takes the output from those models and makes them uniform. Regardless of what type of model you fit, it's going to spit out the exact same format. It's going to spit out a nice data frame. If you wanted to do something like a dot plot of your parameter estimates and confidence intervals, you could just send this straight to ggplot. You'd want to do one more modification, which is create an upper bound and a lower bound by taking this estimate plus minus 1.96 times your standard error. That would yield a confidence interval if it's a symmetrical model like an LM. If it's a logit model, it'd be somewhat more complicated. Yeah, this is nice. Okay, there's another function in Broom called glance. Glance produces data frames filled with fit statistics for the models that you give it. If I run glance on my first linear model, what comes out isn't the parameter estimates of standard errors and things. Instead, it's summaries of the entire model. I get its R squared, adjusted R squared, its overall error statistic is the F statistic, the p-value for it, degrees of freedom, its log likelihood, AIC, and BIC. Tons of different fit statistics, some of them more or less relevant depending on the type of model that you fit, but it's a ton of information, right? You might ask, it's like, well, if I'm running like a model, why would I want a data frame of output for summary statistics of a model? Why should it be in a data frame? I've got like one line here. The answer to that is this makes it really simple to run a very large number of models and do some sort of operation on it. Like, for instance, you might run 50, 100 different linear regressions and then just sort them by one of these fit statistics, and you could do that in tidyverse by arranging on that column. If you were doing output, standard output from like a linear regression, they're all going to be lists. It'd be really hard to arrange those list objects by some subfield inside of those list outputs, but it's very easy to do it if you have a data frame. There's another function in Broom called augment. I don't use this one very much, but some people will probably find it very useful in very particular cases. What this does is it will take some sort of values generated by that model and add them back to the original data used to fit that model. So in this case, this linear model LM1 here, I fit a model that was yn as my y variable and num1 fact1 is my x variables, essentially my independent variables. This was my original data frame here. By running augment on it, it spits out for every single observation in the data an entry for its fitted value according to the model, the standard error of that fit, that residual, what the actual predicted value here, or dot hat I think is actually the standardized value, sigma, and leverage statistics like Cook's D. There's also a standardized residual for it. This is a lot of information that you normally have to calculate in a couple steps. Sometimes you want leverage statistics because that's how you find outliers in your data. Maybe you just want the fitted values out here and the standard errors for each of those fit if you want to plot, say, every single predicted value in your data simultaneously with confidence intervals. You could do that pulling straight off of this data frame pretty trivially. Okay. So the real power here with Broom is apparent when you want to run a bunch of different models at once and get some sort of combined output for all of them. This example here is I've taken the data I'm using today, I have grouped it on values of fact1, and fact1 just takes A, B, or C values, and then I'm saying do tidy linear model this. What do is a function that will repeat whatever you put inside do for every element of whatever you're grouping by. So in this case, what I'm doing is I'm saying we're going to group by fact1. So what I want to do is I want to run a linear model for each level of fact1. So it's going to take all the observations that have, say, fact1 equals A, all the ones that have B, all the ones that equals C, and I'm going to run one model for the group A, one model for group B, one model for group C, take all that output, tidy it up in Broom, and then combine it into a single data frame. So what this is output from a linear model where fact1 is A, this is for B, this is C, and then the parameters inside of each one of those models. I could then compare if these coefficients are the same or different. What this indicates here is you'll see the coefficients are actually basically exactly the same in each of these subgroups. That's because I generated data and fact1 is uncorrelated with my other covariates, so they're going to be exactly the same. So essentially tell us that we could remove fact1 if we wanted to, and these models would come out exactly the same. But let's say you wanted to do this, say, this would be a way to do subgroup analyses, you know, on some factor variable. Let's say you have 50 states in the United States and you want to run a different linear model for every single one of those states. You'd use the same syntax as I did here for 3 levels of fact1. You could run 50 of those models, and then you could subset out which ones, say, have coefficient values very different from the other ones. Those states could have some different relationship among their predictors than the other states in the model. So this is something that might be practical, not if you're doing like a data science model search, but if you just want to run subgroup models on something like national data or something like that. Yeah. Okay. That's all I'm going to say about Broom. Does anybody have any questions about this? It's kind of most of these are niche cases, so I'm not going to dwell on it. Okay. Cool. Broom is the most boring thing today. From here, it's going to start getting a little bit fun, at least in my opinion. I mean, my judgment of what is fun in R is probably very different than yours, but I think it's fun. Okay, so I'm going to talk about ggeffects. But to talk about ggeffects, I need to introduce some vocabulary that some of you are probably familiar with already, but if you're not, you'll be kind of lost as I'm going on. So, an idea we have when we're running models, we're doing data analysis and things like that, is we're often interested in what might happen. That is, what some value of an outcome variable would be if different variables in that go into that model, so different variables in the data take some particular values. And sometimes that combination of values isn't actually seen in our data. There's a lot of common examples of this. Maybe you want to know something like, okay, we fit some time series model, we've got data from, let's say we've run all the way up to 2018 data here, and we just want to know what's going to happen in 2019 and 2020. Our data obviously don't include values for 2019 and 2020, but we might make some assumptions about our data and say that 2019 and 2018 should follow the same patterns as our prior data, but we want to extrapolate from that. Something else might be, okay, maybe we have some particular case in our data that we think is representative in some way. I'm going to show an example later when I'm like, I want to see what is the probability of someone getting arrested if they're black, the person who called the police is white, they're in a white neighborhood, and they were committing a nuisance crime. It's like 4 variables at the same time. That may have never even occurred once in the data set in that combination. It has in my data, but it might not have. I want to come up with, okay, what's the predicted likelihood of being arrested? These sort of ideas that we can set some values to a variable and then get a predicted outcome for it. The values that we set are called in statistics often a counterfactual or counterfactual values. We are forcing our data to take some particular set of values. So this variable equals this variable equals that, and just seeing what the predicted outcome would be based on that model. Because we're interested in the relationship between some particular set of values and an outcome. That's counterfactuals. Okay. For example, it might be something like, we know nothing about some new observation, this is the example I've given before, and our prediction on that estimate might be based on something like we assume every variable is at its mean. If you knew nothing about some new observation that's going to come into your data, the best guess you have on any value at any variable is going to be the mean. It's the lowest possible mean squared error for your prediction. Right? We might just guess everything is the mean and see what our predicted value is when everything is set to its mean. That's a really common case, but it might not be the most useful. Other times we'll have specific questions, like I mentioned before, about what is the probability of somebody being arrested in these specific cases, right? That's a specific combination of variables with particular values, and we want to make some estimate or prediction. We might want to create a plot that has lots of different scenarios on it, plot it so that somebody who's reading my article can be like, well, what would happen in this case? Look at the plot, find that particular estimated probability, which I'm going to show in a little bit. Okay. Providing specific estimates that are conditional on different values of your covariates is a really nice way to summarize the results from a model, particularly if those models have unintuitive parameters. So for instance, if you're running something like a logit model, and the logit or logistic model is going to be my example I use for my more complex example here, you could provide a table of results, but about 95% of people who say they understand logistic regression parameters, log odds, are wrong, and an even higher number of people who say they understand odds ratios are wrong about what odds ratios actually are. Providing people a table of logit model results is often not just like uninformative, but is misleading, right? Does anybody know what an odds ratio is? Odds ratios from logits? So odds ratios would be something like, you'll see something like an odds ratio of 2.5. And if you see in somebody's paper that they interpret an odds ratio for logistic regression as saying it is 2.5 times as likely that thing happens given that variable, that person does not know what they are talking about. That is not what an odds ratio is. An odds ratio of 2.5 says the odds are 2.5 times as high in that given condition, but odds are not probabilities, and they do not have a linear relationship to probabilities, so distrust when you see odds ratios presented in any direct interpretation like that. It's very misleading, because the value of an odds ratio, its probability difference, depends on the size of the groups in sort of the 0 position and 1 position of a binary variable. In a continuous one, it gets really crazy. Anyway, it's much better to instead convert estimates like odds or log odds, or even your linear model parameters, into things like predicted values and the marginal values in plots, because those things can actually be interpreted by a human being correctly. Okay. I've only known one professor who could look at the log odds results of a logit model and directly convert them rapidly into probabilities, and they were an economist, so I still don't think they're necessarily always human. But anyway, so the ggeffects package is in some ways similar to Broom. Where Broom produces tidy model summaries, ggeffects creates tidy marginal effects. So it creates the predictions that come out of a model and puts them into a nice tidy data frame we can plot with something like ggplot. Right? So what a marginal effects data frame is a tidy data frame of ranges of predicted values that you can feed straight into ggplot. When I say ranges of predicted values, it'll be something like, okay, what would be the predicted value from this model across every range of x variables in the model? It will produce a plotted y holding constant every other variable in the model. We'll see some examples here. I'm going to focus on two functions in ggeffects. There's some other functions that are more specialized, but these are the general ones that, honestly, if you want to produce this kind of plot, you'll probably be able to get everything you want using one or basically just this function. This one is kind of behind the scenes. The ggpredict function will compute predicted values for the outcome variable, that is your y variable, your dependent variable, at the margins of specific variables. So you could say something like, I want to know what y is across the full range of this particular x variable, or I want to know what the value of y is if x1 equals this and x2 equals this. Or maybe I want to know what that value of y is when x1 equals 5, but then across the entire range of x2. These kinds of special cases. The neat thing with ggeffects, though, is it comes with a method for ggplot called plot.ggeffects that allows you to pipe the results from ggpredict straight into a plot call, and it will generate automatically a nice ggplot of your marginal effects. You don't have to do any kind of customization of it. It will just spit out the marginal effects you want to see. This makes it very easy to do kind of quick runs at your models, produce readable output for complex models, and get an idea for what's happening. Okay, so ggpredict. When you run ggpredict, that is when you give some model like lm1 to ggpredict, it will produce a data frame with one row for every unique value of some supplied predictor. You have to tell it at least one variable you want ggpredict to range over using the terms argument. So what I've said here is I want to do a ggpredict using linear model 1. My terms are num1. Num1 is just a randomly generated numeric variable. This is saying, okay, I want to create some predicted values from the linear model 1 across the entire range of my num1 variable. This is the only code I presented here. It does this. These are the estimates from that model that ggpredict produces. This is running from the lowest value of my num1 variable, so x equals num1, goes down to about -8. It runs up to about -6. ggpredict has figured out a nice way to space them out so the data frame looks good. It's evenly spaced from very low value to a high value. This predicted is the predicted value of y, given this value of x, holding constant the other variable that was in the model. lm1 had two variables in it. It had num1 and fact1. What it's doing here is it's holding fact1 at its reference value, and then doing a prediction with x at all these different values, providing a predicted y, a standard error for that prediction, and a confidence interval for that particular prediction. Okay? This is nice because this is the exact format I'd want if I wanted to plot my marginal effects in ggplot. I would say I might want a line where my x variable is x here, my y variable is the predicted value, and then I'd want some confidence interval around it, which on the bottom would be the low confidence interval and at the top would be high. We could send it straight to ggplot and do it manually, but but ggeffects will do it for us. If I say plot lm1est, it knows this is a ggeffects object, and it knows how to set the plot up without us telling anything specific, right? This here is the value of num1 as it increases. This is the predicted value of 1. This right here is the coefficient. The slope of this is the coefficient in the model for the num1 variable. This is a marginal effects plot. If somebody wanted to know, on average, what is the estimate for my y variable at, say, x equals 4, they can look straight at the plot and see, oh, well, we'd expect y to be about 3. This is a marginal effects plot. For a linear model, these are kind of boring, because in a linear regression, this is always going to be a straight line. One really nice thing about this, though, over some simpler ways of calculating this, is you will notice the confidence intervals are wider at the ends than they are in the middle. That is because this is actually properly simulating the confidence interval at every point of the data. There's more data at the middle of this model than at the outside, so the confidence interval is narrower at the center than at the end. Doing this manually using primitive methods will result in a confidence interval that's the same across the entire thing, which is incorrect. This does it all behind the scenes without us having to do anything. Any questions about what this represents? It's actually pretty straightforward to use this package. I've got undergrads using this package to do really cool stuff, and they're just like, it's super easy. Okay. You can do a lot of really cool stuff with it, though. So, if you give ggpredict a vector of terms, so here I've said ggpredict terms equals num1 and fac1, it will plot the first term across the x-axis. It will use the second term as a grouping variable. If it's a factor, it will make, say, one line for each level of the factor. If it is a continuous variable, it will break it up into a clean number of approximate breakpoints and draw a line for each one of those, like, pseudo groups. You'll also see here something cool with ggpredict, and thus it's sort of like all the tidyverse type things. I can run a model, pipe it into ggpredict, and pipe it straight into plot, and it will produce this nice output. What this output here, you'll see, is curved. Well, I'm running here a logistic regression model. I'm saying family equals binomial, link equals logit. I'm running a GLM where this is a binary variable, continuous variable, factor, continuous variable. I've made it so we're running along the range of a continuous variable, stratifying it by levels A, B, and C of my factor variable, and it draws lines of fitted probabilities. These are not log odds, these are not odds ratios, these are the actual fitted probabilities, which range between 0 and 100% here. In my opinion, you shouldn't be presenting probabilities as percentages, but still, it's from 0 to 100%. So we'd say something like, okay, for if fac1 equals C, the predicted probability of YB happening at num1 equals 0 is hovering right at about, what is that, 62.5% or something like that. If you provided somebody with log odds, odds ratios, any of those things, they would never be able to get a point estimate for specific values because they would actually have to write out the entire interior linear model in a GLM, exponentiate it, calculate everything out. It's a huge pain. This just presents these nice interpretable results. These are probabilities. People generally get probabilities better than most other things. At 50%, that means it's a coin flip whether the thing happens or not, 50-50. At 100%, it's sure to happen. Right? Nice logit model results. Way more interpretable than any table of parameters you could possibly give somebody. Right? And the syntax for it is very straightforward. Any questions about how that works? Yes?
When I draw this graph by num and fac, what value of num2 and fac2?
It's assuming they're at their mean. If it's a factor, it sets it at its reference level, and if it's a numeric variable, it sets it at its mean. You could specify specific values for those things too, which I'm going to show in a minute. Anything you don't mention, it just attempts to hold it constant. You can't, however, hold a factor at its mean because there's no such thing as a mean for a factor. It's a bunch of different binary values, basically. So it sets it to its reference level. Any other questions? This is something that used to be an enormous pain in the ass to do. And when I discovered this package and saw how simply it does it, it was actually kind of life-changing because I used to spend a huge amount of time plotting these exact sort of things by doing everything manually. And I'm going to show what it takes to do it manually, which will make this package a lot more impressive in a bit. Okay. So, ggeffects can also facet these things out. So if we see something like this is great, but there's a lot of overlap here. It might be kind of hard to tell the difference between this line and this line. This one's fairly clear. If you just add in that plot call facet equals true, it will split whatever the grouping terms are into facets. So here, these are different values of fac1. This is A, B, and C values of fac1, and then the same curve as before plotted on each one of them. So this nicely facets things out. If you give it another grouping term, I believe it will facet it out so that there's two rows. Like it'll go one row for one value of the second variable, one row for the second value of that second variable, and then columns for the values of the first variable. So it'll form a grid of plots. Okay? So it's handy. This is good if you want to get really quick ideas of what is the relationship between different variables in your model and the outcome. I actually, instead of just running and looking at like logit tables or LM tables for my output, if I want to know what is the relationship between two variables and the outcome in my particular model, I just run the model, pipe it straight to ggpredict, select the variables I'm interested in, and spit out a plot. Because I can interpret these sorts of curves a lot more easily than I can looking at like log odds values or something. Because this is automatically using representative values, you don't have to like standardize things, and it's in terms that I understand. That is a probability here, or in a linear model it would be the response for it. If you gave it a count model, like a Poisson or negative binomial, the y would be the counts of events. So it's in the terms that we should be able to understand a lot more easily than weird coefficients like log odds or log counts. Okay? Okay. You could also add, after terms in your terms argument here, you can add specific values here to give counterfactual values to end up plotting or producing predicted probabilities for, predicted values for. So in this case, I've said, I'm going to take the same model as before. I'm going to pipe it into ggpredict, but now I'm saying terms num1, I want to set num1 to -1, 0, and 1, and I want to set fac1 to A and B, and then plot the exact same plot I did before. Now the range down here goes from -1 to 1, which I've set here with 0 in the middle, and I'm only plotting fac1 equals A and B. So from this plot, I've dropped C, and now I'm only plotting this narrow range right in here. This is how you would specify a range of counterfactual values for this if you wanted to be specific. Okay? It's really straightforward in this package. You don't have to go in and modify a data frame and send it into predict manually. You don't have to do any of the math yourself. You just say in a string up here, I want that, and it figures out how to cut that up into the proper values, do all the math behind the scenes, calculate it out, and spit out the plot. This is the kind of abstracted stuff I really like in R, where somebody has done all the hard work for you behind the scenes, right? If you want to do something really complex, you'll probably still have to do it manually, but 9 times out of 10, ggeffects does exactly what I want. Okay. You can also tell it that I don't want specific values, I want it to come up with values of a certain form. You could, in brackets, instead put mean SD and min max, and it will automatically do set the terms equal to the mean and -1 and +1 standard deviation, which is a common thing people want to plot marginals of. What does this relationship look like at sort of representative high, low values and a mean value? Or what does this look like at its most extreme values, its minimum and its maximum? Here I've done both at the same time. So what's happening here is num1 takes values -1 standard deviation, +1 standard deviation. This variable happens to be a mean 1 standard deviation 2 variable. I know I generated it myself. So ggeffects is correctly bringing out 1 - 2, 1 + 2. So right, the standard deviation, it's plotting it. You'll see it's completely flat here. The reason for that is that num2 has been set to its minimum value, -7.59, and it turns out at that minimum value, there's basically a 0 probability of YB. Structured my data like that on purpose. At the maximum value of num2, there's still a possibility of the outcome not happening, but it's pretty narrow, right? So these are representative values you might want. If you don't want to have to look up what the mean and standard deviation is, or the minimum and maximum, you can just say, give me the min-max, give me the mean standard deviation, plot it. This kind of stuff is really good for exploratory sort of visualization of your models. I just want to see what it looks like sort of at the margins. I want to see what it looks like at extremes, all that. Makes your life a lot easier if you have to fit lots and lots of different models and figure out like how they relate. I give ggeffects plots like this to my advisor all the time instead of tables, and he loves it because he can glance at it and be like, That makes sense, doesn't make sense. He has an immediate idea what it is. He doesn't have to sort of look through it and figure it out himself. And he's extremely statistically savvy, so if this works for him, it should work for pretty much anybody. Okay. So, if you feed nothing but factor variables to ggpredict, it knows immediately that it doesn't make sense to do a line plot of factor variables. Instead, it automatically converts it into a dot plot. A dot plot looks something like this. This is values of fact 1, which are A, B, and C. I've stratified it by fact 2, which takes a value of red or blue. And these are the predicted probabilities with confidence intervals at those values of those factors. I didn't have to tell it I want a dot plot. I just said, here's some factors, and it knows that if they're factors, it should be a dot plot instead of a line plot. It just knows, just works, right? It's the kind of package I like. I don't have to tell it anything. It knows what I want. You could tell it specifically you want other plot types and things. Or, instead of sending it directly to plot, you could send it into ggplot and do something more complex with it manually, because this is just outputting a data frame that could be plotted using any other ggplot function. Does that make sense? It's pretty straightforward. I highly recommend using this for plotting your model output. I would say if you run basically any model in R, there's no reason not to do some marginal effects plots to figure out what's going on. It should just be one of those things you always do. Okay, some notes on ggeffects. It has a great vignette, great documentation, and a lot of things it can do. I recommend reading it, looking into it. Other things it could do predicted values for polynomials and interaction terms. Interactions are very difficult for people to interpret normally. Even a linear model interaction is usually people are interpreting it wrong. We just had a job talk in our department last week where somebody interpreted interaction effects incorrectly. If somebody says something like, oh, well, we have this interaction here, this is the main effect, this is the interaction effect, they don't know what they're talking about. There is no such thing as a main effect in an interaction effect. The effect in an interaction term is the first derivative of the combination of the main parameter and the interaction. If you interpret it in any way other than that, you don't know what you're talking about and should probably go back to a stats class. So, I saw that in a job talk. I was turned off because that person was coming in, theoretically should be teaching methods classes. Don't know how to talk about methods? Get out of my job talk. Okay, so that's really nice. Interaction terms are hard. I'm going to show plotting 4 interaction terms simultaneously in a minute in a complex example. It'd be impossible to do that any other way than doing it visually. Okay. Other things, ggeffects works with a ton of different packages. There's only a couple packages I've ever used that ggeffects will not produce results for. And in fact, as of a couple weeks ago, it just added one of those 2 packages to it, which was Lavon for structural equation modeling. The fact that ggeffects can do Lavon predictions is insane, because doing predicted values for structural equation models is really hard. Now it just does it. It's amazing. Another thing, of course, is that you can send ggeffects objects to ggplot calls and freely modify these plots, do whatever you want with them. If you ran this plot here, I could say, like, this looks like a standard ggplot sort of output. Maybe I want this in theme, theme minimal or theme blank. I could literally just add plus theme minimal to this. Because it's a ggplot object, it will change the theme. You can imagine this is like a ggplot call that has the AES in it and everything, but it's constructing it for you. You can add things to it, just stick it on. If I want a different title on here, I could do plus ggtitle, call to it, and it will change this plot. It's just ggplot under the hood. Okay. Any questions on ggeffects, its capabilities, what you might use it for? I think it's one of the best packages I've ever seen in R. I think everyone should use it and try it out if you're doing any stats. If you're not, today's mostly a wash. Okay. So, I'm going to go into a more advanced example here. All the way back in week 2, I presented a plot I had in a recent article I worked on as an example of using ggplot to present a really challenging, complex plot in a way that's still readable to like a general audience. The article's right there if you're interested. This particular model is modeling the likelihood or the probability that somebody gets arrested who is the target of a police contact, conditional on what neighborhood the contact happened in, the race of the person stopped by the police, and the race of whoever called the police in the first place, because we had data on who called the police, which is the rare thing in the paper. Normally you don't have information on the individual people who called the police, but we had all those data in this particular case. So the model for this is actually a simplified version of the model, but the model has arrest, which is a binary outcome as a dependent variable. It has those variables I've mentioned up here, the logit model. The complex thing about this is in addition to having a ton of different variables, including contextual variables like % black, % other, disadvantage, the year in the data, that kind of thing, those things are PBL, POT, disadvantage are characteristics of the neighborhood they were in. In addition to having a ton of covariates, there are 4 different interactions happening at the same time here. There's an interaction, an assumed interaction between the race of the target and the caller. That is, maybe somebody's more likely to be arrested if the caller is white and the target is black than if it was just because them being white versus black. So there's something about if a caller is a particular race, it impacts the probability when it's an opposite race person, cross-race contacts. There might be an interaction between the type of crime and the race of the caller. That is, maybe if the caller is white and it's a violent crime, it might be no more likely for the person to be arrested than if it was a black caller. But if it's a nuisance crime and it's a white caller, they might take their complaints more seriously. There could be an arrest interaction there. Maybe there's interaction between the type of neighborhood and the target race. That being something like maybe a black person is way more likely to be arrested in a white neighborhood. Hint, that's true. And there might be an interaction between crime type and neighborhood type. Maybe they take serious crimes less seriously in a black neighborhood than they would in a white neighborhood or something like that. These are all interactions. Thing is, that is a lot of interactions going at once. That table is impossible to understand because every effect in that table is conditional on the level of some other variable. You could put that on a nice, beautiful table. No matter what you do with it, it's going to be useless to try and interpret that table directly. The reviewers still wanted the table, of course, because people love fucking tables, but it's basically impossible to interpret. So what I wanted to do is produce some kind of plot that looks like a ggeffects plot. I might want something like this, where I say, take that model, and then I want to see what the predicted probability of arrest is across whether the suspect, that is the target, is black, whether the complainant, that is the person who called the police in the first place, is white, and what type of neighborhood they're in. This plot says this is stable white neighborhoods, black disadvantaged neighborhoods, changing neighborhoods, and then this is if the person who is being targeted by the police is black, if they're white, and if the complainant is white versus the complainant is black, so the person who calls the police. This is already a really complex plot with a lot of stuff going on, but it still only covers 3 of the 4 interaction terms that I want. So I'm assuming the other interaction is sort of held constant or ignored. Okay? There's a ton of information here, and this is a plot that, I actually think is, if you think about it, is really informative, and there's something interesting going on here. For instance, you see here that this is essentially if the target of police action is a white person, it doesn't really matter whether the caller is white or black. Their arrest probability is pretty similar. But if the target of police attention is black, it really matters whether the caller is white or the caller is black. This is essentially saying that for a black-on-black crime, the police are just way less likely to arrest you. But for a white person calling the police on a black person, they are getting arrested. That thing up there is basically bordering damn near 100%. Right? This is something that has a lot of implications for the current news, things going on in the United States. Right? But I'm leaving out the entire story about my crime types and my neighborhood types. Okay, so ggpredict can only handle 3 variables in its terms argument at a time. If you want to do more than 3 variables, that is, if I want to capture all these interactions at once, I'm going to have to do something else. ggpredict can't handle it. No way I can swing ggpredict will make it work. For this particular article, I wanted to plot estimates across counterfactual values of all 4 variables that occur in my interaction terms. Those variables are the race of the caller, the race of the target, the crime type in that neighborhood, and the type of neighborhood it is. We had a neighborhood typology system derived from multivariate latent class mixture models, which you don't want to know about, but that's actually a pretty robust thing. Question is, how could I plot all 4 of those variables at the same time? The answer to that is the wonderful combination of some statistics knowledge, some math knowledge, and some code, which produces love. It's going to be wonderful. It's going to be a bit of a roller coaster, but this is useful information if you ever want to do something like this, or if you just want to know how ggeffects actually works. Okay, this is going to be some of the only statistics I get into in this class. Do stop me if you have questions about it, because this is stuff that is interesting that I can pretty much guarantee you've never encountered before, except maybe if you've taken Chris Adolph's MLE class. Okay, so let's say we run some sort of model. In my example, I'm using a logistic regression model. Type of model is very common. Pretty much everyone fits a logit at some point. If you consider that for any type of model, for the most part, any type of model with some mild exceptions for structural equation models or hierarchical linear models, the predicted values of y are just equal to the x values, the observed x values, multiplied by your estimates of your coefficients. X times b equals predicted y, right? Where x is a model matrix and beta are coefficients. Okay? It's pretty common, like everybody knows if you multiply x times beta, you get a predicted y. In this case, x could be any arbitrary number of variables. In my particular case, it's like 15 variables are in there. There's 15 coefficients here, and the predicted values are going to be equal to however many values of x I take, that is rows of data. Okay, beta, this might be in terminology unfamiliar to some people, but beta is not just, like, betas are not a fixed thing. Your estimated coefficients, your estimated parameters in a model are themselves random variables. It's just one particular realization of a random variable. Those random variables have some estimated distribution, which is described by the model's variance-covariance matrix called sigma. Standard errors are obtained by analyzing the variance-covariance matrix of the parameters, and the more stable it is, that is, the tighter it is, the smaller your standard errors are. For a really distributed variance-covariance matrix, your standard errors are very large. Okay? Any questions about that? If you take an intro stats class, that's pretty straightforward. Okay. Using this knowledge, the knowledge that predicted y's equal just x times beta, and that there's a distribution of our parameters that's a variance-covariance matrix, we can leverage this to do a lot of cool stuff. What we can do, and what we're going to do, is we're going to extract the model matrix X. That is the actual values in our data for all of our different observations for all of our variables. We're going to get the estimated coefficients from our model. We're going to get sigma from our fitted model, sigma being the variance-covariance matrix of our parameters, that is, of the betas. We're going to make lots of random parameter draws that are going to be centered on our predicted our coefficients and distributed according to sigma. We've done like R norm to do random draws from a normal distribution. What we're going to be doing is we're going to simultaneously draw a parameter value from every one of our betas, and their distribution is governed by something called a multivariate normal distribution that's based on our variance-covariance matrix. Then we're going to multiply each of these draws by some counterfactual x values. That is, we're going to set x to particular values. We're going to leave everything else at its mean, and we're going to get a whole bunch of predicted y values, like 10,000 of them. Then we're going to get a confidence interval by saying, I want the middle 95% of those predictions. If our parameters are roughly correct and we have a variance-covariance matrix, due to the central limit theorem, if people remember that from their first stats class, this confidence interval between the 2.5% and 97, that should be 0.5% quantiles of these predicted values, that will be exactly the confidence interval for our parameters, or for our predicted values at a given, like, x's with our model, like, parameters. Okay? This is complex. It's okay if that doesn't make any sense. I'm going to show you all the code to do it, which can be replicated for almost any type of model you could possibly run in R. This method right here produces a simulated mean and a confidence interval at every value of x that we use. So it does those nice kind of bell-shaped confidence intervals of our data structured that way. This method of obtaining confidence intervals and means is referred to as the percentile method. If you've heard this, it is a type of bootstrapping. Bootstrapping just means we get some parameter estimates from a model, and then we use a whole bunch of random draws and use those to summarize something. Bootstrapping just means lots of simulation. Bootstrapping is usually the easiest way to get like confidence intervals on something. You can get them algebraically for many types of models, but not always. Bootstrapping is just super easy to do because computers are really good at doing random draws and doing math on a huge number of random draws. Computers are not very good at coming up with algebraic solutions to problems. Okay, so the way we're going to do this is we start out, as I've mentioned here, that we need a whole bunch of random parameter draws that are centered on B and they have some distribution from our variance-covariance matrix. So what we're going to do is we're going to make a whole bunch of random draws, basically using a function like rnorm. If you remember, rnorm takes two arguments. The first argument is the mean that you want to have everything centered around, and the second argument is its standard deviation. This function we're going to use is called mvrnorm. It's in the mass package, which comes with R, but it's not a base package. It takes these parameters. It takes n, the number of draws we want to make. As a simple example, I'm using 10,000 draws, which should be fast on anybody's computer. I would usually use 100,000 or something like that for most models. It takes mu, which is a mean. But this mean is a vector, because what we're doing is we're doing random draws from a multi-dimensional space. We're going to draw from, say if this model had 4 parameters, 4 betas, 4 different variables that are predicting our outcome, we would draw one value for all of those variables each at the same time. If there's 4 variables, we do 4 draws at a time. It's going to take our parameter estimates, our coefficients from the model, so coef mod arrest. Mod arrest is the name of the fitted logistic regression model I did earlier. And then it's going to take sigma. Sigma you obtain from a model using VCOV, variance-covariance matrix, on that model. I just say MVR norm, 10,000, these coefficients, this variance-covariance matrix. What pops out? A data frame with 10,000 rows. It's actually a matrix with 10,000 rows. It has one column for each parameter in our model. So it has one for the intercept, right, the constant term, one for white victim. This was, is it a white person who called the police? Is it a black person who was arrested? Crime type nuisance, so on and so forth. You'll notice all of these are a little bit different. These are random draws. It basically figures out how all of these different parameters are correlated with one another, and then does a random draw from the probability space for all these parameters at the same time. It's complex, but what this is doing is it's capturing the fact that maybe when this particular variable is high, all these other ones tend to be high too. So you don't want to just draw one randomly at the time and then assume the other ones are independent of it, because they don't, they are actually completely dependent on each other. They're correlated in some way. MVR norm is necessary to get random draws that are correlated with each other in some way. That's all we're doing. What we get here are 10,000 rows of parameter estimates. Okay? These are just parameter estimates, right? We aren't at predictions. This is just saying the intercept is, might be 2.7, might be 2.9, might be 2.6. This is an estimate of what our model's parameters would look like if we got new samples. We add another sample, it might be different by a certain amount. We do a different sample, it's different by a certain amount. This is quantifying the uncertainty that would come from using different samples. Okay. The next thing we need is we need a data frame that has the counterfactual values that we want different values for. We want, that is, one row each, or one scenario per estimate we want to plot. If I want to do a predicted probability for every combination of variables, and I have 4 variables, I want, in this case, I want to take 2 times 2 times 2 times 3 estimates. The reason is, this is a binary variable, this is a binary variable, this is a binary variable. My neighborhood type takes 3 categories. If I want every possible combination of those 4 variables, I want 2 times 2 times 2, 8 times 3, 24 scenarios. If you're doing binary variables, this is really easy. If you have continuous ones, you're going to have to figure out breakpoints and stuff like that. Okay. There's some limitations to what I'm going to do here. I don't want to get impossible values. This particular variable, the third one, is mutually exclusive with other ones. It can only take a value of you can only have one neighborhood type at a time. I have to remove it. What I do here is I say my counterfactual values, my x values, are first going to be equal to the mean of every variable in the data set. That's a good starting point, just being like, what would happen or what would be the predicted value if everything is at its mean? That's sort of, if we knew nothing about it, this is what we would expect to see as a probability for arrest. Okay? Then I come up with the number of scenarios, and I make a data frame with a number of rows equal to the number of scenarios. Because in ggplot, every row of your data turns into one plotted point, or one part of a line. Well, I want to do 12 estimates, 12 points on my graph. I need 12 rows in my data. These are just going to be the x values I've done here. The number of rows is equal to the scenario. and their names are equal to the names that are in the data. I basically created a data frame that looks exactly like my whole data set, but every value in it is held as mean. So all the values in each column are exactly the same. I then populate a new data frame here called CF my counterfactual values, which are going to be here. I've done permutations. I probably should have done something less complex here, but basically, imagine that you wanted to get every possible combination of a bunch of dummy variables so that anything, it's an example. So, imagine that you have 3 dummy variables. I'm going to call them D1, D2, D3. You want these to be able to take, like, all of them be 1, that one be 0, this one be 0, like that, 0, 0, 1. All of these different ones are unique combinations. Unique combinations of things are called permutations. This was a quick way for me to get permutations of all of those simultaneously. You could do this manually and create a matrix of your dummy variables if you wanted to, or select specific values. And this is a little bit complex, and you're like, I ain't never doing this shit, and that's fine. But just know that that's all I'm doing. I want to know that I need a predicted value when all these dummy variables are this, when they're all this, when they're all this, when they're all this. I want some predicted y in all those cases. I'm just doing it for a lot of variables at the same time. This method will hold using any kind of variables, any kind of dummy variables that you ever put into it. You can use this code to do it. Next thing, I remove some impossible values, like I said before. My variables in column 4 and 5 are mutually exclusive. They're neighborhood types. Something cannot be both a white stable neighborhood and a black disadvantaged neighborhood. So anytime that those two add up to 2, that is, they both take a value of 1, I've removed the rows. I give those columns some names that are those. Then I assign them back to my counterfactual data frame. Okay, this is fairly abstract. This is what we get. If I do a glimpse of my X data frame, the variables I want to vary over are things like white complainant witness victim, takes values of 1, 1, 1, 1, 1, black rescue suspect 0, 0, 0, nuisance zeros, victim you'll see goes 0, 0, 0, 1, 1, 1. These are just different permutations of all the combinations of the variables I'm going over. All the ones that have long numeric values right here are ones that are at the mean. You'll see this is the same value here and here, and here and here. Those are held at the mean of the data. So I'm holding all of these at their mean and varying only the ones that I'm actually interested in plotting values over. So I have this giant data frame, but most of these things have values that are being held constant. Okay? There's one problem with this, in that the interaction term, white complainant witness victim, black arrestee suspect, these right now are being held at their mean. Because I'm plotting over my interaction terms, I need to modify this so that this interaction term only takes a 1 if both of these variables are 1, and otherwise it takes a 0. I do that by doing a really quick mutate, saying, okay, our main variables are right? The interaction terms have some specific form that looks like this. I'm just assigning them the actual mathematical values they should take. This variable is named that in the model. I want it to be equal to the product of these two things for all of that. This is a clunky way to do it, and I could have done it in a more elegant way, but I'm doing this because it's illustrative. And also, it's easier to tell if I messed something up. If I do that, I have the exact same data frame. My interactions are now fixed. So we would think, and this is a check. You always check if you do some kind of weird, complicated thing like this. This variable here is the interaction between nuisance crime and changing neighborhood. I look down here, it takes a value of 1 in this particular location. Well, I know that if that takes a value of 1 there, my neighborhood should be a changing neighborhood. I look up at changing neighborhood, it's a 1 here. And then the crime type should be nuisance. I look up at nuisance crime, it's a 1. If I look over here at crime type nuisance is a 1 here, but changing neighborhood is a 0, it should still take a 0 down here. This is just knowing that the interaction terms I've created match my counterfactual expectations. Okay. So I have this big data frame, tons of information in here, but the important thing is I've made it so that the only variables that differ across different rows of my data are the counterfactuals that I'm interested in. Every other thing in my model doesn't matter to me, so I've made them all exactly the same. This is holding them constant, which is what ggeffects does on everything except the terms you specify. All right? Okay. Now we need estimates, right? All this has managed to produce is a data frame of new data. We have to take those counterfactual values and multiply them by our parameter estimates to get predicted values. That's all we're going to do. I say here, our simulated parameters. That is the massive data frame, 10,000 rows long, however many parameters are in our model wide. I just say matrix multiply sim parameters times our counterfactual values. And this is going to produce a huge matrix of simulated log odds coefficients. I probably shouldn't have picked a logit model for this because it produces log odds, but why not pick the most complex example possible? If I look at only the first 6 rows and 6 columns of this data, it looks something like this. These are predicted log odds for each of the counterfactual values in my data. This data frame is gigantic, okay? This has 10,000 rows and 24 columns. Each column is one of those predicted, or one of those counterfactual scenarios. So what here was like this column right here would be one counterfactual scenario. Each one of those generates one column in our data and 10,000 rows because we've done 10,000 random draws of our parameters and just multiplied that times our counterfactuals, right? So we have this massive data frame. You're like, well, what the hell am I going to do with a matrix that's 10,000 rows long, 24 columns wide, that contains a whole bunch of multiplied out log odds? You're like, how useful is that to me? Because what we want are probabilities, right? We don't want people to have to interpret log odds or odds ratios. Instead, what we want is we want predicted probabilities because a human can interpret predicted probabilities. Most humans, save my old economics advisor, cannot interpret log odds directly. To do that, we need to know this relationship, which I'm going to go through relatively fast. Basically, the odds are equal to the log odds exponentiated, right? Inverse of a natural logarithm is the exponentiation. A probability is just equal to the odds of something divided by 1 plus those odds. In our math, if you want to convert a log odds to a probability, you just exponentiate the log odds here and divide them by 1 plus the exponentiated log odds. That produces a probability. I just converted this entire matrix, the sim log odds, remember, 10,000 rows, 24 columns wide. I can just spit it in here on both sides, and then if I look at the first 6 rows and 6 columns, these look like probabilities. A probability has to be between 0 and 1. These are all really high because the probability of arrest is really high, but these are predicted probabilities. So I've done a little bit of basic math. Basic math, depends how much time you spend converting log odds, but I have now predicted probabilities. These are different predicted probabilities of arrest, one for each scenario in my data, so every counterfactual value, and then for each counterfactual, 10,000 different predicted probabilities, okay? So let's say we're interested in scenario 1. How do I summarize 10,000 draws from it in some useful way? I just want to get what is the mean of that draw and what are its quartiles. To do that, I'm going to do a quick function. I'm going to grab the mean and 95% confidence interval from our simulation estimates. I create this function, extract PECI. What this says here is I'm interested in a value. I'm going to give it one argument. This argument is going to be an entire row of my data. That is all of the predicted values, 10,000 of them for a particular counterfactual scenario. From that, I want to extract the mean of that vector, and then I want its 25th or its 2.5th percentile and its 97.5% percentile. I'm going to assign names to those values, a PE, LB, and UB, that is a point estimate for the mean. LB is the lower bound, UB is the upper bound. So it'll spit out, if I give it a vector that's length 10,000 or 100,000 or a million, it's going to spit out 3 numbers. The mean of all of that entire vector, the 2.5% percentile, which is a lower bound of a 95% confidence interval, and the upper bound of a 95% confidence interval. Because even though we simulated 10,000 numbers, the only thing we care about is the point estimates and the upper and lower bound. So if I take my simulated probabilities that I did before, and I apply my extract PE function to that along the columns. Do people remember how the apply function works? We used it in 2 different weeks in this class.
That's
Apply, like lapply, sapply. Yeah. In this case, I'm just using the normal apply function. What this says is that, okay, in this case, I have a really big matrix. I have some function I want to run on parts of that matrix. What I want to do is I want to run extract PECI, the function I created right here. I want to run it once on each column of my data. So I say, these are the data. 2 is the second margin of something. The first margin is its rows. The second are the columns. So 2 says, do this over the columns. Run this function. That is going to output something. In this particular case, it's going to output something that has 24 columns. I want 24 rows, so I transpose it. This will take something that has 24 columns, it's real wide, flip it diagonally. I now have 24 rows where each column is point estimate, upper bound, and lower bound. I want it as a data frame. And I'm going to call it estimated PEs. Then I'm going to add some things to it. Basically, I have these 24 scenarios, but what I do not have in this matrix is what was the actual value of those variables that we used to get those like counterfactual predicted values. I'm just adding this back on. I'm just saying, okay, there's some value for the reporter, the person who called the police, some value for the target, who the police were called on, for the crime type, and for the neighborhood, and I'm going to base them on the values from my counterfactuals I created way back, a while back, because I created them using these variables. I say, okay, if the reporter was any white person, I want this to take the value, or if it was a white person, I want to take value any white. If it was a black person, I want to say all black. Do that for all of these different ones. It's more complicated with case when, because I was storing disadvantaged neighborhood in column 4 and changing neighborhood in column 5, and if it's neither of those, it's a stable white neighborhood. That's what happens when you have factor variables. Okay, you're like, okay, well, what the fuck does this make, right? This is what we get out as a result. If I take my estimated point estimates, I rounded them so they're easier to see, but this is otherwise exactly what this entire operation has been to get. I have, for 24 different scenarios, I have a point estimate, which is the mean. That is what we would expect, all things being equal. This is what we think is the likelihood this person gets arrested. A lower bound and an upper bound, that is a 95% confidence interval around that estimate. And then we have a bunch of other variables we can use in our ggplot to plot these in the correct locations. This is if the reporter is black or if the reporter is white, if the target is white or black, if the crime type is serious or a nuisance, and if the neighborhood is stable, white, changing, or disadvantaged. And what you'll see here is I have every possible permutation of these 4 variables represented in this table. This one varies the fastest, that is it goes stable, white, changing, disadvantage, stable, white, changing, disadvantage. This one goes serious, 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 nuisance, 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 serious, serious, serious. 6 whites, 6 blacks, and then 12 blacks, 12 whites. This is every possible combination of those variables with a corresponding point estimate, lower bound, and upper bound. This is actually what ggeffects does behind the scenes. All of those operations together is what is done in a single call of ggpredict. This used to be, right here, on all that math I showed you, the only way to do this in R. You can now do it with ggpredict and set some values. And if you want to do it over 4 variables, you're stuck doing it the way I just did it, which sucks. But now you've seen it. So what can I do with this? Well, it turns out I can do a lot with it. What I did is I plotted these point estimates and the upper bounds and the lower bounds. I stratify them on the target, reporter, crime type, and neighborhood variables all at the same time. This is the ggplot code from week 2 to generate that plot that I showed in class. This says I'm going to use the estimated point estimates I just created. I'm going to say my aesthetics are X is target, Y is a point estimate. We're going to group by reporter, and I'm going to facet it simultaneously by the crime type and the neighborhood. I want to have G on point, that is the point estimates are going to be dots, and then G on error bar will make little confidence interval bars that extend out from those dots. From there, I just specify some manual values, like if the reporter is a white person, I want the dot to be white. If the reporter is black, I want the dot to be black. I give it some titles, and I customize where the legend is to get it out of the way of my data. Okay, there's a lot going on here, but every single one of these things in here is something that we've been introduced to in class. It's pretty straightforward. I haven't talked too much about error bar because I don't do stats in this class except for today, but this just generates those error bars. This is the plot that we created that would have been impossible to create with ggeffects or any way other than doing a ton of math. So what this is the probability of arrest for a person contacted by the police if somebody called the police on them by the race of the reporter and the target, the neighborhood it occurred in, and the type of crime that the incident was. Right? There is a lot going on in this plot. It's conveying a ton of information, right? You can say, like, okay, well, this plot up here is the likelihood that somebody gets arrested if they are black, a white person called the police on them, it happened in a stable white neighborhood, and it was a nuisance crime. And that is the exact probability with a confidence interval for it. So they've got about an 87.5% chance of being arrested in that particular condition. Good luck getting some kind of precise, easy to communicate thing like that from any table of coefficients for a logit model, let alone even a linear model. People would have to calculate all that stuff out. This kind of data, this is what people actually want when they read a paper and you have some logit model. People care about what is the probability of something happening. They do not care if it has a log odds of 1.45 on something. They want to know, if you put all these things together, what is a meaningful interpretation? I can look at this and say, well, the interpretation here is, if it's a nuisance crime in a stable white neighborhood, a black person is this much more likely to be arrested. Like, a black person is this much more likely to be arrested than a white person. That's for a white person, that's for a black person. That is a big difference. That is a difference of 10, 13 percentage points. 13% more likely to be arrested, and they can just see that by looking at this plot. If they had to calculate that out, good luck. Okay. If you put plots like this in your papers, they're a lot more likely to get published because people like pretty pictures and you can convey a ton of information. If you didn't know how to do this, you would have to take every one of these like different variable ones and probably make different plots. And most journals don't like it if you make like 8 plots because it eats up a huge amount of the page count. Sometimes they count a plot as being like 400 or 500 words. That's chopping into your paper a lot. I managed to get 2 different models that were that complex with all those interactions into exactly 2 plots in this paper, which freed us up to have 38 pages of text, which was pretty nice. Okay. Steal my code, do this if you ever want to do anything like this, and if you want help doing it, email me. I like doing this stuff, and I think this is how stuff should be presented in papers. Tables are bad. I believe they should be cut out of most papers or put in an appendix. Okay. Any questions about that? That is the only brutally complex thing I'm going to go over today. From here, it's all nice and coasting. Okay. Okay. Evangelical part of the class over. Now we're going to talk about making tables, which I put after that because tables suck. But people want tables, so let's talk about tables. So, if you're doing something like a simple R Markdown document, some HTML output, it's for a class or something like that, and the formatting doesn't matter too much, we used Pander to make data frames, but Pander will also handle most models. GLM models, LM models, I think it might handle HLM models, but I'm not sure. It will handle also the summaries of those models. I'll load up Pander. If I run my linear model, my first linear model that I ran, I give it to Pander, this is the table that pops out. It just takes the coefficients, that is like here, estimates, and the parameters, intercept, weight, horsepower. This LM1 here is, I don't think I actually ran it directly. This model, LM1, is actually the linear model for the MT cars data set. MPG, weight, horsepower. I must have done that hidden. Interesting. Sometimes I don't go through my own slides enough. It's been too busy. Anyway, this Pander table has an estimate, a standard error, a t-value, and a p-value. It's a little bit nicer than the raw R output. It's nothing special. I had a couple questions from people about why in my slides the lines of my Pander tables alternate between purple and white, and they don't do that in your documents. That is a pure idiosyncrasy of the format that my slides are in, which are in Sheringan. The default style sheet for HTML alternates purple and white in my tables, and I've been too lazy to change it. If you want yours to be purple and then white, it is a pain in the ass to do. I will give you the code if you want to do it, but it requires modifying the style sheet for the document, so it has a little bit of header addition. Anyway, I got to get rid of that so it doesn't confuse people. Okay. You can also give Pander the output from LM summaries. What this does is it gives you the same coefficient output here, and then adds below the number of observations, residual standard error, the R squared, and adjusted R squared. Tells you, again, what is the model being fit. So these Panda tables are okay. If you're going to do like a little memo to hand your advisor or something like that, these are usually sufficient, right? It's really basic, but it works. These Panda tables, however, look a lot nicer in PDF documents. If you give them nice variable names, they come out looking pretty nice. They're ugly in HTML, they're real pretty in PDFs. I use Panda ones for PDF documents if they're quick pretty often. If I'm going to do something I really want people to look at, or, God forbid, it's for publication, I'm going to do them with LaTeX. Don't learn LaTeX, it will destroy your life. That's what you have to. Panda is good for that. They're not what I call publication ready. They're not really pretty. They're not the sort of thing that I want to show anyone I want to impress. There is another package, sjplot, for producing HTML tables and the sort of tables you'd actually want in memos and things like that, that look like the tables in journals. They're pretty. They look really nice. sjplot is written by the same author as the ggeffects package. He just writes these packages that are really nice for sort of the day-to-day things that actual statisticians and social scientists like me do, which includes sometimes giving people tables. So, the function tab model in sjplot, you just give it a model. In this case, I've given it linear model, the same one as before. I put it in tab model. It comes out instead looking like this. This looks like more like the kind of tables you'd see in a journal article. The dependent variable is on top. There's beta. There's a confidence interval for it. The p-value. You know, things are nicely separated by horizontal lines. The number of observations, r squared, adjusted r squared. I didn't give it any options. This is the default output for it, and this is something that I'd be perfectly happy to hand to somebody I know to, you know, if I wanted tabular results from something. I hand my advisor things just like this out of models. He's like, these are great. It's perfect. No options. It comes out looking nice. This is a theme with the sort of packages this particular person who writes sjplot and ggeffects. His stuff is made to look with all defaults, look pretty nice so people can look at it. It's good for being lazy, and a lot of programming, in my opinion, is about being like really effective while being really lazy. Okay. So, often in journal articles, you will see a single table that has 2, 3, 4, 5, 6, 7 models, right, that you can compare. Normally it'll be something like some simple model, they'll call it like a naive model or something like that. They'll set up some straw man like someone would believe that naive model. And then from there they'll keep adding variables to make more complex models going right from left to right. Okay? Well, in sjplot, if you want to make multi-table models, you do the exact same thing. You just say tab model and then keep giving it model objects. Model 1, model 2, model 3, any number of models. And it then automatically organizes them in the order you provide them in, and organizes the parameters, right, so that the same parameters in the same location. Even if you fit different models where the parameters are out of order, it rearranges them for you. It puts them out, and then you can do things like, oh, well, we start with this naive model, we add some variables, we can see the r squared is increasing, that kind of thing. Maybe there was missing data on one variable, it would show if the observations drop, right, because you'd lose observations to missing data. You can see how the parameters change going left to right in this model as you add correlated variables. It also, by default, will even tell you, like, the factor variable, it's the level here, 1, is in reference to 0 as the reference category. It provides some automatic stuff. It's kind of neat, right? With some options, you can also have it give different names, automatically capitalize the names or format the names here without you having to do it manually in the data. It's a really cool package for being really lazy, which is basically everything I love in programming. Okay. Questions about this?
Can the SJ table to make each models all the figures of all the number of each model in one column rather than in 3 columns?
Oh, so you want to do one, so the model's like stacked?
Yeah, just like those journals table and put stars rather than p-value.
All those are options that you can do. So normally the models will always be in separate columns. You might be able to transpose it in some way so you have different models and then parameters going across them, but I've never tried to do that. You can have it give stars instead of that. My personal preference, and this is a very strong preference for reasons I'm going to explain, is it is usually best to provide in a linear model like this, it's ideal usually to provide the standard error and maybe a confidence interval. Maybe a p-value, stars, whatever. I actually like the p-value itself. Whenever possible, confidence intervals are really good to have, especially if it's not a linear model. Anytime you see a table, somebody presents like a logit model, and they provide like not log odds, but they provide odds ratios and a standard error. Standard errors don't make any sense for an odds ratio because they're not symmetrical across the odds ratio. You can't do plus minus the standard error with that. So they should provide a confidence interval for it. By default, this provides sort of the most useful information, which is a confidence interval and a specific p-value rather than stars. This is what I like, but you can tell it to do anything. It has a huge number of options. Another really cool thing about SJPlot, which I don't talk about today, is you can actually give it a custom HTML, like CSS style sheet to format this in different ways if you want. It's really cool. The disadvantage to that is SJPlot does not work in PDF documents. So it's for like online memos and stuff, not so much publication. But if you're actually going to publish something, you should be manually doing your tables to some degree. Any other questions? Okay. So the SJPlot package does a ton more than make pretty tables. So I showed pretty tables because I think it's one of the most useful things, but that is a giant package with a huge amount of functions that do a lot of cool things. Yeah, I recommend looking at the website for it. SJPlot is more complicated than ggeffects. Everything that was in ggeffects I showed today can be done in SJPlot with slightly different syntax. You can also link them together. It does a crazy amount of stuff for kind of making publication-ready data visualization. It's pretty awesome. Every one of the graphical functions in SJPlot is based on ggplot, so you can also add and subtract from them using the syntax we've used in class. So you can produce some in SJPlot and then change its theme and things like that by doing plus theme to it. So an example of things it can do, it does Likert scale plots. So if you work with ordinal data, often like scales 1 through 5, this is a really good way of presenting that sort of data. So if you have, let's say, a bunch of different survey questions, in this case, question 1, 2, 3, 4, and 5, there's some things you want to do with this kind of ordinal data. You want to run it from a range. In this case, it goes from strongly agree to strongly disagree, but don't knows do not lie inside of this thing. You tell it what values are don't know, and it automatically sets it over here. So these are like non-answers. These are valid answers. It centers them 0, where the positive answers are going to the right, negative answers are going to the left. These are a really good way of summarizing ordinal survey data. It's a type of plot you rarely see people do. It's the best way to do these, in my opinion. SJPlot makes it really easy to do these things. It's super cool. Another example, SJPlot does really nice crosstabs. Okay? In this case, this is some data where you're cross-classifying the data by 2 different variables. We've got elder's dependency here, carer's level of education, and then this crosstab has given us a count right here. It's also giving us, in this case, I believe, these are column percentages, and these are cell percentages. Okay? And notice they're color-coded. It's easier to see on like a computer screen that has a little bit better contrast than this one. But color-coding things by rows makes it much easier to say, okay, I want to compare this percentage to this one. Your eyes will track by color. This is something that there's good cognitive science and perceptual science behind this, knowing that we can track things like from one space to another by color. Makes it really easy to do quick comparisons across things. It also provides summary statistics on this crosstab, like its chi-square value, degrees of freedom, the p-value for the whole table, all of that. I think that's is that the non-centrality parameter? I don't know what that is. But, yeah, nice crosstabs. Right? This is just like a really simple call. Another cool thing about SJPlot, you go down the website, it has workable examples with produced code for every one of the types of plots it can do. So you can basically just format your data the same way as the example, and then run the function using his provided calls, and produce these nice like tables. Okay. This is the kind of crosstab I would love to see in a journal article, like formatted like this. It's beautiful. And also, it's automatically calculating all those percentages. The only thing it's being fed, I think, are the counts. All that other calculation is doing for you. Okay. So, another thing I'd like to briefly talk about. If you want to do nice tables in a PDF document, you're going to have to play at least a little bit with some LaTeX. To do that, I recommend one of two packages. There's Stargazer or Cable Extra. The Cable Extra package lets you construct complex tables in either HTML or LaTeX using syntax that looks like ggplot. You do add this, you add this, you add this, you pipe through it. Stuff like that, it produces nice tables. Stargazer looks more like more conventional R stuff where you give it data and then a bunch of arguments and it will produce a nicely formatted LaTeX table. Stargazer is fairly idiosyncratic. It has some kind of weird arguments, some weird defaults, but it produces really beautiful tables. It's a good way to do it. Cable Extra requires more thought because it doesn't produce anything you don't ask for. It's kind of like a ggplot. You don't add a geometry, it doesn't plot anything, right? One of these two, if you're going to be doing a lot of tables and PDF documents, learn to use one of them. If you want to edit LaTeX documents and say you want to see what that table looks like when it's produced in LaTeX without rendering to PDF, or with rendered PDF, you can make and use LaTeX syntax in R using Sweave documents, which are .rnw. If you go up into like File, New File, RStudio, you can do Markdown documents, but you can also do Sweave documents. Sweave documents have to be written entirely in LaTeX, so I don't recommend them for normal human beings, but sometimes if you need to do pure LaTeX, it's the only way to do it. Another alternative is you might work in a dedicated LaTeX editor. Overleaf is a 100% online, works through your browser LaTeX editor and project management solution. If I'm doing pure LaTeX documents, I do them on Overleaf because Overleaf automates the process of like downloading necessary packages. LaTeX is a nightmare for package management and stuff, so Overleaf is pretty good for it. I do my posters on Overleaf if I do PDF ones. Lately I haven't been doing much LaTeX stuff if I can avoid it. R Markdown, though, supports a lot of basic LaTeX syntax, so if you don't need to get really fancy, if you're not really anal about the way that like your formatting looks, you probably don't need LaTeX and you can do it in R Markdown with a little bit of LaTeX syntax. You know, formulae and stuff like that, you can do in R Markdown. Tables actually come out pretty nice in R Markdown if you write them in LaTeX. Another approach you might do is to manually format LaTeX tables, but use inline R calls to fill in the values. This is nice because it will make a table that looks exactly the way you want, but if the values in your data change, it fixes the table for you as you go. As long as you don't add or remove a variable or something like that, it will still work. I do this for some reproducible documents when I have a really specific way I want the table to look, or when I'm doing structural equation models, which don't always have established nice methods for generating pretty tables. Here's a bonus one. This didn't fit in anywhere else in the term as a function to use, but it's something I find really useful, and as it turns out, I provide output from this to my advisor all the time on projects, and he loves this, so I'm going to show it. There is a package called CorePlot that has all these different functions for generating correlograms. Well, hard to say. Correlograms are ways of visualizing the correlations between variables in some data set. The way they work, you'd load CorePlot, run a correlation. You could do it on an entire data set. In this case, I've done correlation on the MT cars data set. I have some arguments here, which don't matter too much. They're going to customize how it looks. But if I just run CorePlot on some correlation matrix, it generates something that looks like this. What this is a color-coded correlation plot. If I want to know what is the correlation between, say, the variable gear and the weight variable, I can see that that correlation is negative 0.58. It's color-coded red because it's negative, and the circles get bigger as the correlation gets stronger. If you have a lot of variables in a data set and you want a quick view of all the correlations, this function is invaluable. It's super cool. It's way better than looking at the table of correlations. It's just great. If you do a lot of correlation-based modeling, like structural equation modeling, these tables are amazing because you can immediately see what things you might want to have in the linked to other variables, what things you don't. And very often, at least with my advisor, as soon as I get some data set, he's like, give me a correlation table. Give me a correlation table, because his brain works entirely in correlations. I spit out these things, and he's like, oh, this is beautiful. He loves it. It simplifies our meetings greatly. This is nice because it has this scale from 1 to -1. You can also tell it to organize the data in particular ways, so it can put all the positive correlations on one end, all the negatives on another end. It has sorting and all that. I love this function. It's like one little function and one little package. Super useful. Okay, so that is 100% of the content for this class. We're done. Well, I'm going to have some parting thoughts in our last 5 or 10 minutes here. So, what have we learned in this class? Depending on how much knowledge you came into this course with and how much of the fire hose of shit you managed to get out of here, you might have learned a lot. So, we learned how to get data into R from a variety of formats, things like CSV files and stuff, but we also talked about Stata files, SPSS files, that kind of thing. We also talked a little bit about generating data through simulation. We've learned some things about being a data custodian, manipulating and cleaning data, reshaping data. We learned actually a lot about making pretty visualizations using ggplot. We spent a lot of time with ggplot, and you've probably learned more about it than you think you did. Yeah, we learned some automation with loops and functions, some vectorization to get around doing loops. We know about combining text, calculations, plots, and tables into R Markdown reports, which is the basis for reproducible research. Learned a lot about that, probably more than in any other class you'll take on this campus. We've also learned a little bit about acquiring and working with spatial data if you came in for the spatial lecture. And something I forgot to add today is a little bit more on visualizing model results. Used to be some stuff on social media, but it's all out of date, so it's not up here anymore. So what comes next? Well, if you haven't already, you're probably going to take some statistical inference classes. Other classes in CSSS, and I'm going to provide some sort of like suggestions for things you might want to take, and if you ask me, I will provide frank assessments of all of those classes, because I've taken basically all of them. You might want to learn functions for doing hypothesis testing, models like hierarchical models, machine learning, survey design, all that kind of stuff. All those functions are usually very easy to use once your data are clean or tidy. They are a nightmare to use if you don't know how to arrange your data nicely. So now that you've been through this class, hopefully you're in a little bit better shape to go into those classes and actually use those techniques. Now, we've also learned a little bit about accessing output from those models you might learn in those classes, whether that is working with lists or today using broom and ggeffects and similar stuff. I recommend continually practicing with this stuff. If you set R aside for just, months or something like that, you're going to lose what small amount you manage to actually collect from this class. You need to keep working at it constantly. I would recommend doing things like take things you've already done in Excel, SPSS, or Stata, replicate them in R, take something that you know what the results should be, see if you can get the exact same thing. Or, as often has happened to me, I will go and replicate something and realize that 3 years ago I did it completely wrong. Maybe it got published, and I'm like, shit, now I gotta go, email somebody, which has happened. Think about your data using dplyr and tidy data principles. Even if you're not actually working on it, just think about how you can structure things. Think about how to arrange, your data, and also make your future projects easier to arrange in a nice, tidy format. If you're thinking about how to construct a survey or something like that, think about the back end, the way the data are recorded. Why not try and record them in a tidy format to begin with so you don't have to do any data manipulation? I try and get my Google Document stuff to spit out tidy data so I don't have to format it myself. It's kind of nice. Use R Markdown for reproducibility. Another thing I recommend doing, I use R Markdown to make all of my slides, even if there's no R code in them. I use it to make all of my memos, even if there's no R code in them. Just keeps me up on it constantly. Everything I spit out is always a memo. I just write them in R and R Markdown. Makes really pretty looking things without me formatting it. It also prevents me from ever having to use Word, which is really nice. Or PowerPoint, or any of those things. More advanced stuff, I would recommend, especially if you're going to, eventually go on the market, either private sector or the academic market, pick up version control. You might do it in RStudio, you might do it with an application, but make a GitHub, put your projects there. It's a good way to store your stuff. You can even host your personal website on there. Maybe you want to do interactive stuff with shiny web apps. So this might be something for your own use or something hosted that other people can use. I just had a student email me today who came out of this class, and she's doing web app shiny stuff and brought me this really sophisticated thing. And I was like, this is somebody who literally learned R in my class 2 terms ago or something, is now doing shiny web development stuff. And it's I need help with this. And I'm like, well, 1, this is super damn cool. Two, thanks for following my suggestion. Make some Shiny apps. They're really cool. Shiny apps are ways to do interactive things. Like, let's say you want a plot that you can select what variables you want to plot and like what values you want to plot, but you don't want to do any R code. You can just have sliders and buttons on a little browser window, and the plot will change as you change values. It's pretty cool. It's how people do little analysis front ends. It's actually kind of how Tableau works. Behind the scenes, it's doing all the data manipulation and stuff by you pressing buttons and pulling sliders and stuff, but really it's basically like a Shiny app. Other things, this is a really advanced kind of, but you might want to write your own functions and put them in an R package so you can use them all the time. I do this myself because I use a lot of stuff really consistently, like the %not_in operator, which for some god-awful reason is not a default R operator. It's in there just so I don't have to type it in every single time. Okay. So some plugs. If you're going to take future CSSS classes, I really ought to start adding CSE classes and stuff in here, but for now I know CSSS classes and social classes. If you have no stats background, you've taken this class, but you don't have any stats at all, Social 504, Applied Social Statistics, is a good class for a general statistics introduction. If you have sort of basic stats, but you want to go up to at least just general linear model, Social 505 is next term, taught by Jerry Herding. I'm the TA for that class, so if you want to take that, next term, Social 505, okay. I'm the TA. I love that class because it's a general linear model, and I get kicks out of teaching that class. It's great.
Which one is that?
Social 505, it's Jerry Herding's, it's not this one, it's the one after that. It doesn't require 504, but it's basically the class on basic regression. Linear model and general linear model, maximum likelihood.
What day of the week is it?
It's probably Tuesday, Thursday. Yeah. It's good. Probably the best basic regression class. If you want to learn more about social science computing, this is going to be offered again, we're hoping next year, big data and population processes. Maybe not. Good class. If you've only finished Social 506, which is the class after this, maximum likelihood with Chris Adolph is pretty good. It's a good general maximum likelihood class. If you want to do visualization, when I say master it, I mean master from the perspective of the cognitive science behind visualization and not just the programming. How can you best display particular types of data or results? Visualizing data is pretty good. If you want to study events or durations, event history analysis is great. And when I say events or durations, very commonly people just want to know whether something is going to happen or not. It turns out most models that people think to use for modeling whether something happens or not are not actually appropriate for modeling that. A logit model that maps whether something happens or not over a span of time, you can't just run a logit on that because very often something would have happened but you haven't been watching long enough. You have to model that time process at the same time. Similarly, if you want to model how long it takes for something to happen, you have to model it differently because often you're not watching long enough. It might be a duration, but if something, you don't know, the thing never happened in the span. A good example is let's say you want to see how long people live and you study it for 100 years. If somebody lives over 100 years, you don't know when they died. You can't validly study the duration of that. It's also not valid to drop that observation because it would bias your results downward. Event history is really important for working with those sorts of problems. I also think the event history class is a very good introduction to maximum likelihood. It's an incredibly good one, so it's a great class to take for general maximum likelihood. If you want to work with network data and network modeling, there's a social network analysis class. There's also one via eScience that's really good. Network data, if you're going to work on if you're interested in the connections between units, what predicts things being connected or not connected, or diffusion processes, things passing from one unit to another, it's network models. Lastly, if you want to work with spatial data, and especially if you want to do inference with spatial data, spatial statistics is the way to go. It's not an easy class, but as it turns out, it's really not easy to robustly model things that occur in space because you tend to have autocorrelation processes that occur in multiple dimensions at the same time. That is basically two things near each other tend to be alike. Things that are far apart are less alike. That's about it. But you're modeling that not just in a distance this way, but in 360 degrees. That's complex to model. It kind of looks like doing time series, but if you're doing time series moving in two directions at the same time. In fact, if you think about it that way, that's exactly what it is. It's time-space models. It's complex, but if you're going to do geospatial stuff, you have to do that if you want to do those statistically correct. Any questions about classes? Anything like that? Okay. So, thanks for coming to my class. I hope it's been useful in some way. I hope it hasn't been overwhelming. If it has been overwhelming, tell me in the evaluations. The evaluations have gone out. I recalibrate my class every single term by reading all those evaluations. I copy it all out. I make a list of things to do every single term. So I really appreciate them being filled out in detail. Tell me what worked, tell me what didn't work. Just tell me if you don't like my face, that sort of thing. That's perfectly fine. I'll read all those things. I will take them personally. But yeah, please do. I use them. I really like this class. I want to be maximally useful to people without completely overwhelming people. I feel like people should be standing on the edge of the cliff but not falling off to get as much information as possible in the hopes that later you will come back to this material when it's useful over and over again. So rather than do like a whole bunch of relatively easy stuff that every single person in the class knows thoroughly, at the end of this class you should be like, I've been blasted with information, but you can come back to it and do it. Okay, so with that, thanks for coming. It's been a great term.
Thank you.
Yeah, thank you.
Do you need to run to get food, or can you answer questions?
I can answer questions.
Yeah.